really just use your DC, the DC component. So for using DC component, we already have this, Beer-Lambert law in red light and Beer-Lambert law in infrared light. If we play the same trick, we can get rid of D. We play the same trick, then we can get rid of D. It looks like this works. So if you start to think about StO2, this might be the first way you try if you have learned about SpO2. You might want to try this, but it turns out this is not going to work because the Beer-Lambert law only applies to a single uniform absorbing medium. But tissue is multi-layered, heterogeneous, and scattering. So strictly speaking, Beer-Lambert law doesn't apply to tissue. So in pulse oximetry, since we are really just looking at the shallow arterial blood, the delta D part, so the law still largely holds accurate. But for NIRS, we are looking at the bulk of tissue, so it's not accurate to use Lambert-Beer law. So we have to go with something else. And it turns out, that in NIRS, we need, 2 LEDs and 2 PDs. So how many LEDs and PDs do we use when we do SpO2? Do you remember just a few slides ago? How many LEDs?
3.
3
LEDs and 1 photodiode.
Correct. So, but in NIRS, we need 2 LEDs and 2 PDs. So we have 2 LEDs, red light and infrared light. Then we have 1 PD and another PD. So this is the setup for NIRS. And to do NIRS calculation, so we first want to define optical density. That is how well a medium attenuates light. So let's assume that let's see. So light travels from the source to a photodiode, and this zero loss, no light is lost. Then first, the optical density is defined as the ratio of transmitted light over incidental light. And then we take a log. So if there's zero loss, what's the optical density? Zero loss. Transmitted light equals incidental light. What do we get here? Transmitted light equals incidental light. What's the optical density? Okay, it's 1 inside the parentheses. Then we take a log. Zero. Okay, yeah, 0. So, when optical density is 0, that means there's zero loss when it travels through the medium. But, for our tissue, there's loss. So, we define the, optical density here. So, and it turns out there's a relationship that applies to our tissue. So, we are not going to go deep into why this works. We can find it in the literature. Let's look at this equation. So in the left hand, we have 1/3 1 minus h lambda. H is a constant. Lambda is your wavelength. Then we have a square of something. So in the square, we have natural log 10 times the derivative of optical density with respect to distance. Then minus 2 over rho. So rho is the distance between your PD and your LED. And on the right, we have something, we are familiar with. So natural log 10, K, where K is a constant, then epsilon times C plus epsilon HB times CHB plus epsilon HBO2 times CHBO2. So the term on the right is something we are more or less familiar. But the term on the left, we have a derivative. How can we know the derivative with respect to distance? This is not something engineers are quite comfortable with. So how can we get this? So engineers like to do approximations. So the way we do it is to have two photodiodes. We have two photodiodes and we measure optical density at two different locations. So the derivative is can be approximated as, optical density at location 1 minus optical density at location 2 divided by the difference of the two distances, low 1 minus low 2. This is how engineers approximate derivatives. Are we comfortable with this? Using two PDs to get the derivative. Yes.
How would you check if that's a good approximation? I just have to trust it.
Yeah, you have to do some optimization to, tune the distance. But, engineers just like approximations. So yeah. So, yes, this is device engineering. So you have to do some optimization of the distance of the, PDs to the LEDs. There's a lot of optimizations you need to do here. Okay, so we get the approximation of the derivative. Then we plug this in. We got this equation again. So in this equation, we have two unknowns, the concentrations. Then on the right, this is essentially our sensor data. We have like H, constant, non wavelength, and optical density. Optical density we can get optical density from our light intensity. So the term on the right is essentially our sensor data. So again, two unknowns, one equation. So in theory, we can get StO2, like SpO2, because in StO2, we really just need their relative ratios. We just need their ratio, right? So we don't need to know the absolute values. So in theory, we can just use this single equation at a single wavelength to get StO2. But since we have the capability to have two LEDs, that means we can have two of these equations at two different wavelengths. Then with two equations and two unknowns, we can solve for the absolute values. So NIRS gives you the absolute concentration of oxygenated and deoxygenated hemoglobin. So NIRS is going to give you the absolute concentrations. But for the purpose of StO2, we just need the ratio. So one LED is okay, but we have the capability to get their absolute values. So that's why we use three LEDs in use. Okay, quick summary. So we discussed three different techniques: PPG, pulse oximetry, and NIRS. PPG measures heart rate, and pulse oximetry, which is a special type of PPG, measures SpO2, and NIRS measures